All right, we're going to finish off chapter 4 today. Continuing our discussion about experimental design. You'll see what we're dealing with here is some things that you can add to your experiment to make it a better designed experiment. So we're skipping all the way to the top of page 22 because there's a lot of activities and examples in there. So in an experiment, we have what's referred to, get back down there. Okay. In an experiment, we have what's referred to as blocking. Okay, blocking in an experiment is very similar to stratifying in surveys. Now, it's important that you know the terminology and that you don't confuse the two. Stratifying occurs in a survey, how you're obtaining your sample. Blocking occurs in the experimental design. Okay, but they both do the same type of thing. So blocking accounts for a source of variability, just like stratifying. This means that blocking is a good way to improve the experiment when appropriate. Blocks, similar to strata, are not formed at random. You choose what you're blocking on, and the best variables to block on are the ones that are the best predictor of the response. And you want to block on things you can't control. So let's take a look, and we're actually going to do this example in the notes. All right, it says a popcorn lover wants to know if it's better to use the popcorn button on her microwave oven or use the amount of time recommended on the bag. To measure how well each method works, she will count the number of unpopped kernels remaining after popping. She goes to the store and buys 10 bags, each of 4 different varieties of microwave popcorn: movie butter, light butter, natural, and kettle corn, for a total of 40 bags. Explain why a randomized block design might be preferable to a completely randomized design. So in a completely randomized design, we would just take all 40 of the bags, randomly select out half of those bags, and then those half of those bags would go to the microwave button option, and the other half would go to the time option. However, there's an issue with that, because what if all of the movie butter and light butter went into the popcorn button, and the natural and kettle corn went into the time category? Then I really wouldn't be able to determine if it was the button or if it was the type of popcorn that was causing the difference in the number of kernels that were there. So a completely randomized design ignores the differences between the 4 types of popcorn. The randomized block design would reduce the variability in the number of unpopped kernels. Oops. By accounting for the differences in each type. So So at this point, you might be a little confused exactly what blocking does. But we're going to go through and we're going to design out this experiment to help you kind of understand how blocking works. So the easiest way to outline this is via a picture. Okay? So we have our 40 bags. We're going to do this with a block design. We have our 40 bags of popcorn. If I was just doing this as a random design, I would then randomly assign half of them to the button, the popcorn button, and half of them to a time. But here I'm going to block, and this is where the blocking occurs, right here. I'm going to take it and I'm going to divide them up into each of our brands. We have brand 1, which is our movie butter. We have brand 2, which is our light. We have brand 3, which is our natural. And then we have brand 4, which is our kettle. This step right here, where we've done this, this is your blocking step. You've blocked come on. Okay? Based on the type of popcorn. So I've separated them up, similar to what you would do in stratifying. You've separated them based on their type of popcorn. And now you're going to randomly assign each of those, half of each of those different brands to the button and half of them to the time. Okay? So this step right in here is the blocking step, where we've divided them up based on their type of popcorn. Now let's keep going with our experimental design. So after we've done this and we've divided them up, we're going to randomly assign each of these to our two different groups. So group 1 and group 2. So now I've got all my movie popcorns, the 10 of each of those. Half of those are going to group 1, half of those are going to group 2. And I'm going to do the same thing here for the light. So I'm going to randomly assign half of them to group 1 and half of them to group 2. I'm just abbreviating here, randomly assign your natural, half of those to group 1 and half of those to group 2. And then the same thing for your kettles. Group 1, they're receiving the button, the popcorn button. And group 2, they're getting the time. And then the same thing for all of the others. So button and time and button and time. And then finally for the kettle, button and time. So you can see by blocking, you're ensuring that the popcorn that's getting the popcorn button, you're going to have the movie popcorn, the light popcorn, the natural, and the kettle, and then same thing for the time, okay? We've ensured that we're getting half in each of those by blocking based on the type. Once I've done all that, now I'm going to bring everything back together, and I'm going to compare my results. And see, is there a difference on the number of unpopped kernels based on whether we use the button or the time? But that's the key thing on blocking. You block on a variable that you can't control, and then it's like you're stratifying, except blocking occurs in an experiment, and stratifying occurs in how you've obtained your sample. Here's another example. We talked about the pillows and the amount of hours you sleep and doing an experiment on that. We could block based on gender. We think gender might impact how often you sleep. So when I get all my people to be part of my experiment, the first thing I'll do is I'm going to block on gender. So I'll have the males here and the females here. And then amongst the males, I'll randomly assign, a third of them no pillow, a third of them one pillow, a third of them two pillows. And then same thing for the females. That way I'm ensuring that I have both males and females in each of my treatment groups. Same idea and same concept here. We'll answer the question about the best variables to block on in the caffeine experiment in class. Let's talk about another type of experimental design, which is called a match pairs design. So a match pairs design is a randomized block experiment in which each block consists of a matching pair of similar experimental units or similar subjects. There are two ways in which you can create a match pairs design. It's very often that you'll see a match pairs design with twins. If you're a twin, you're like a hot commodity in experiments. So in a match pairs design, chance is used to determine the order, or which unit rather, I should say, in each pair gets each treatment. Sometimes a match pair design consists of a single unit that receives both treatments. Since the order of the treatments can influence the response, chance is used to determine which treatment is first for each unit. So let's talk about a match pairs design for a second. There are two ways in which you do a match pairs design. The first way is that you pair people that are very similar, most commonly twins. And you create a block within each individual pair. And then within each pair, you give one person one treatment and the other person the other treatment. So you've paired them up, okay, in that regard. And then you can compare their results. So I might give one twin, maybe we're seeing, does music affect your score on an IQ test or something like that? So I might give one twin music to listen to during the test and one twin not music to listen to during the test. Now, another way in which you can do match pairs that is perhaps even a better technique is that each individual person receives both treatments. So again, if we go back to our example with, the taking a test with music and without, one day I might have you take an IQ test listening to music, and then the next day I might have you take it not listening to music. And then I'll check the effects of the music on your score, and I can compare against yourself. Well, the best comparison you can make is against yourself. Okay, that's another way. When a single unit receives both treatments. In that case, it's very important that you randomly select the order in which the treatments are being done. I shouldn't have every single person in my experiment take the IQ test with no music first and then with music second, because they might kind of have some familiarity with the test by the time they're taking it with the music. So I should have half the people take it with music first and half without, and then the same idea, vice versa. Okay, so it's important that you randomly assign the order in which people are receiving those treatments. So again, in a match pairs design, each student should receive both treatments, but in a random order. Okay, this is going back to our pulse rate example there. Final thing to discuss is now we've gotten our results, how do we use them? What do we do with the results that we've gotten? Okay? So the scope of inference refers to the types of inferences or conclusions That can be drawn from a study. So we've collected all of our data. Now what do we do with it? Remember, you can only show a cause and effect relationship in a well-designed experiment. The types of inferences that we could make about the population and inferences about cause and effect are determined by two things. And those two things are random selection and random assignment. If you've randomly assigned people to treatment groups in a well-designed experiment, that's when you can show cause and effect. Most experiments, you can do this. If you randomly selected from your population, meaning you have a representative sample, then you can generalize the results to the population. So those are the two things you have to keep in mind. Random selection, we can generalize to the population. Random assignment, we can show cause and effect. So here's a little chart to help you out. Were the individuals randomly selected? Were the individuals randomly assigned? If they were randomly selected, then you can show inference about the population and generalize your results there. If they were randomly assigned, cause and effect. So if both are done, then yes, you can do both of these things right here. You can show both inference about the population and cause and effect. It's kind of rare that that would occur because it's rare that you can randomly select people to be a part of an experiment, which is what you would be doing in this case here. So this is kind of doesn't happen too often. Were individuals randomly selected? Yes. Were they randomly assigned? No. This is frequently what you see in an observational study. In this case, yes, you can show inference about the population. No, you cannot show cause and effect. Were individuals randomly selected? If the answer to that question is no, you cannot make an inference about the population. Oops. I'm going to put it over here because it keeps shooting. So no to this. I don't know why it's going down there. But yes, you can show cause and effect if they were randomly assigned. That's where most experiments fall. So no inference about the population, yes inference about cause and effect. And if you've done neither, which some observational studies are, you haven't randomly selected your group and you haven't randomly assigned them, then you cannot show either thing. You cannot show cause and effect, and you cannot show inference about the population. So always think to yourself, did I randomly select? If the answer is yes, you can generalize to the population. Did I randomly assign? If the answer is yes, you can show cause and effect. Well-designed experiments randomly assign individuals to treatment groups. However, most experiments do not select experimental units at random from the larger population. Therefore, most experiments you can show cause and effect, but you cannot generalize to the population. On the contrary, like we said, most observational studies don't randomly assign individuals, which rules out inference about the cause and effect. However, observational studies that use random sampling can make inferences about the population from which they come. Okay, so make sure that you're aware of that. Last things here. A well-designed experiment tells us that changes in the explanatory variable cause changes in the response variable. However, lack of realism can limit our ability to apply the conclusions of an experiment to the settings of the greater interest. So if I've done this experiment in kind of a lab setting that's controlled in many regards, sometimes it's not ideal to then explain the cause and effect relationship that's occurred. In some cases, it isn't practical or ethical to do an experiment. Consider these questions. Does texting while driving increase the risk of having an accident? I'd have to assign people to text and drive and see whether or not they cause an accident. That's not ethical. Does going to church regularly help people live longer? Does smoking cause lung cancer? I can't randomly assign half my population to smoke longer, or to smoke rather, and then half the population to not. So in lots of these cases, you do observational studies and you ask them, do you smoke? Do you text while you drive here? So in that case, we cannot show cause and effect, but we might show that there's an association between our variables. Association does not imply causation. That's when you see studies or you see headlines that say something like, smoking leads to a higher rate of lung cancer, or this eating, some type of food leads to higher cholesterol or something. You're not creating experiments here that have shown cause and effect. You're showing an association, which is not causation, because there can be other factors that are influencing your results. So in general, association does not imply causation. And it's important that you realize that. Okay, the only time you can show causation is in a well-designed experiment. And in all of these examples up above, those are not going to be experiments, and therefore we cannot show that cause and effect relationship. We'll go through lots of examples in class as well as some free response questions. I'll see you then.